Math 1332, Chapter 7, Consumer Mathematics, Section 7, Compound Interest, Video 6, Annuities. Now, you probably know what an annuity is, even if you've never heard the word annuity. But let's think about how people retire, because so far all we've talked about is compound interest, where you take a chunk of money, let it sit there for a long time, and at the end you see how much interest has grown. It's a good idea, but here's the problem. If all you're going to do is drop money down at the beginning, you need a lot of money to invest at the beginning. So is that how people retire? Do they just run across a huge chunk of money, throw it into some interest-bearing account and walk away, then 25 years later walk back to see how much it's grown into? You could do that, but the problem with that plan is that you need a big chunk of money up front, and most of us don't have that. So how do you pay into your retirement? All of it up front? No. Most people, when they pay into some sort of retirement fund, they make regular payments that are smaller over the duration of the investment. Most people who have money taken out of their check for an IRA or some type of investment, that's an example of an annuity. So really an annuity is an investment where you don't put all the money up front, but rather you make regular payments into that annuity. An annuity is a savings investment plan in which the investor makes a regular fixed payment into a compound interest account where the interest rate doesn't change during the term of the investment. This differs from a regular compound interest account in that you don't invest an entire amount at the beginning of the investment period, but rather break the investment up into smaller payments. For example, you might pay $500 annually for 3 years into an account that yields 6% interest compounded annually. The total amount accumulated, payment plus interest, is called the future value of the annuity. I do want to point out something in this last paragraph that's kind of subtle yet important. There's actually two different time structures that we're looking at here. How frequently do we make payments, and how frequently is interest calculated? Most annuities, the frequency of the payments matches the frequency that interest is compounded. It's not impossible to have different time structures there. For example, you might pay $500 annually, but the interest is compounded monthly. But for the sake of simplicity, at least for this class, we will always assume that the frequency with which you make payments is the same as the frequency with which interest is compounded. And we'll kind of assume that they occur at the same time. You can also think of an annuity as a sequence of compound interest investments. Remember, compound interest investment is you put the money down, you walk away, you come back at the end and see how much money you got. So here's why it's a sequence of compound interest investments. You make a payment. At the end of some time period, interest is calculated and added to the principal. At the same time, you make another payment into the principal. So, and I'm pretty sure this is how it goes. Interest is added, another payment goes in. So that second payment hasn't drawn interest yet. So you put the first payment down, and then at some point in time, interest is added and you make another payment. At the end of the next time period, interest is calculated and added, and another payment is made. So it's this game of money sits and draws interest, and when it draws interest, you make another payment. Then it draws interest, and you make another payment, and so on and so on. This repeats until the end of the annuity. It is cumbersome to calculate the interest at the end of each payment period. For example, if you're making monthly payments into a retirement annuity for 25 years, that's 12 years times 12 payments per year times 25 years equals 300 payments. So imagine doing the compound interest formula 300 times in a row, even with technology. Luckily, there is a formula that gets right to the end of the annuity's future value. So let's take a look at it. Future value of annuity. Suppose you pay into an annuity, and here's all the parameters in play. You make N payments per year. So the N here kind of has the same flavor that it did in the compound interest formula, because in the compound interest formula, it represented the number of times per year interest is compounded, but we're assuming that every time interest is compounded, we make a payment, so it's the same. Each regular payment is capital R dollars. I think the capital R there is for regular payment, regular periodic payment. The interest rate is still lowercase r, so here's where you have to be careful. This is usually not good form, but sometimes it's necessary in math problems to have a capital version of a letter and a lowercase version of a letter represent two different things. This is one of those cases. The term of the annuity is still T years. So we have number of payments per year, number of years, amount of the payment, and the interest rate. Then the future value A is given by the following formula. All right. To calculate the future value, it's a long fraction, so buckle up. The numerator starts with the monthly payment, or I'm sorry, not the monthly payment, the regular payment, because you may be making payments 4 times a year, twice a year, once a year, or more often than monthly. But you start with the regular payment, and then it's multiplied by not 1, but 2 open parentheses. This first open parentheses, or rather the inner parentheses, looks like the compound interest formula. 1 plus r over n with an exponent of nt, because it is. But after that, there's a minus 1, and then close the parentheses. Now, if you're wondering where the minus 1 comes from, I would have to go into an algebra discussion about the sum of finite arithmetic sequences. And just the fact that I said those words probably makes you go, never mind, I'll just trust you, there's a minus 1 there. Then the denominator is just r over n. So it's the same fraction that was in that part of the numerator. Make sure I didn't botch something up. All right. So as you can tell, this is a pretty sizable formula. And it's got the same issues with parentheses that we had mentioned in the video about calculator usage. First off, this formula has a fraction where both the top and the bottom are more than a single number. So as a consequence, I strongly recommend writing an extra set of parentheses around the top, although technically speaking, they're not necessary here, and a set of parentheses around the bottom, which are necessary. I don't know why I'm doing this. So I'm going to put extra parentheses around the entire numerator and the entire denominator because they are larger than a single number. And we have the exponent again with more than a single number in it, so we're going to put parentheses around that. Now, this looks like a pretty big mess, but the advantage to writing the formula like this is if you're very meticulous, you will never make a mistake putting it into your calculator unless you mistype a number, so try to avoid that. So a pretty sizable formula. Let's do an example. You would like to retire at 65. You are currently 40, so 25 years to go. You start paying into an annuity that pays 5%. If you make monthly payments of $250 into the annuity, how much will you have when you retire? Assume the term is exactly 25 years. And I say that because when I say you're currently 40, you might have turned 45 months ago. You might have turned 40 maybe 3 or 4 months ago. And then when you retire at 65, maybe it's 65, and then 3 months later you retire. But we're assuming the term is exactly 25 years. And on the bottom, you see we've got a follow-up, how much interest was earned. All right, so let's write down all the parameters that we have and see what we got. The annuity pays 5% interest, so our lowercase r is 5% or 0.05. We're making monthly payments, that's 12 times a year, so n is equal to 12. Our payments are $250, that's capital R. I really wish you could use capital P for payment, but P means principal. This isn't principal. Principal is everything you put up front, and that's it. These are regular payments. How much do we have when you retire? Assume the term is exactly 25 years. So we have T is equal to 25. Now, hopefully, if you're in my class, you're taking notes. And hopefully you wrote down that formula. But if not, pause the video right now and write it down because I'm about to use it on the next page. All right, so what would it look like? I invite you to put it in your calculator and try to beat me to the answer. All right, if we were to set up the formula with all the values, we got the giant open parentheses at the beginning, and then we start with our monthly payment, our regular payment, which is $250, times double open parentheses. And yes, it does matter that you put both, trust me. 1 plus the interest rate, 0.05. over the n, which was 12, close the parentheses, exponent, 12 times 25, close the exponent, minus 1, close, I believe it's a double close parentheses. Let's go back and check. Yes, it was 1 parentheses, but when we marked it up with the extra parentheses for the numerator, it did end up being a double close parentheses. And in the denominator, we have open parentheses. We have open parentheses R, 0.05 over N. Now, I know what some people are going to be tempted to do. Let me get out my calculator and figure out this answer, round it off, then add 1 to it, and then raise it to the right power. It's going to be ugly. Let me round it off, then multiply by 250, and then blah, 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 blah. The problem with doing intermediate steps is that most of these division problems, and it starts with a division problem right there in the middle, most of these division problems will not come out to be a finite decimal. It will go forever, forcing you to round off. And trust me, rounding off internally in these calculations is going to cause a large enough error at the end to get your answers marked wrong. Because let's say that you calculate this and rounded it off to 3 or 4 decimal places. You lost a little bit of accuracy, but when you raise that inaccurate answer to the 300th power, that little error compounds into a large error, and now your answer is going to be too far off. So your best strategy for getting the right answer, or at least the answer the homework is going to look for, is to put the entire thing in your calculator in one move and then round at the very end. Now, how do we do that? This is the whole reason I draw all the parentheses, so that you can type in exactly what you just wrote down, top to left to right, top to bottom, exactly what you see. Just remember to type the times after the 250 if your calculator needs it. If it doesn't need it, that's okay, but it's never wrong to type the times there. So in your calculator, you would type open parentheses 250 times double open parentheses 1 plus 0.05 divided by 12, close parentheses, exponent button, open parentheses, 12 times 25, close parentheses, minus 1, double close, divided by open, 0.05 divided by 12, close. And all I did was literally read it left to right, top to bottom, and wrote down exactly what I saw. If you're in my class, I highly recommend writing not only the formula, but what you're going to put into your calculator, so that when I grade your test, if your answer comes out wrong, I can look at your work. If this were a test question and you wrote this down like this and your answer came out a little bit wrong, you're going to get most of the credit because you're demonstrating that you set up the problem correctly, and then lose just a little bit for the calculator usage. Speaking of which, I invite you to, if you haven't done so already, put this in your calculator and see what you get. I'm about to pause the video so I don't waste your time typing it in. I got a future value of $148,877.43. I'm going to pause and calculate it again, just in case I get a different answer. If I get the same answer, I'm going to assume that I did it correctly both times. And using a different calculator, I got the exact same answer. Because this is a dollar amount, rounding to 2 decimals makes perfect sense. Did you get that dollar amount? If you didn't, go back and check your work. And if you're still having trouble getting it, contact me. One comment and then one follow-up question, and we're done with this video. My first comment is this enough money for you to retire on? Do you think after you stop working, you can live the rest of your life on this amount of money? The answer is probably not, unless you plan on not living very long. I know it sounds like a lot of money, but even if you made $50,000 a year, this isn't even 3 years. So it kind of raises the question, what can you do to increase the future amount? Well, there's a lot of things you can control, some of which you can't. You can't control the interest rate, the bank does. You really can't control how often the interest is compounded, the bank does. But you can control the monthly payment. And you can control the term, or at least you might have some control over the term. But the one thing you really have the control over is the monthly payment. What do you think would happen if we doubled the monthly payment? In other words, what do you think would happen if instead of $250 our monthly payment were, oh, I don't know, 500. That's double, because math, you know, says so. Do you think it would just double this amount? Well, I'm going to pause the video and recalculate it with a monthly payment of 500 instead of 250 to show you what happens if you double a payment. I invite you to calculate it too. Actually, of course, it's going to double the payment. Duh. Why? Because if I do this at $250 a month and you do this at $250 a month, collectively we're paying $500 a month. We each would make the $148,877.43. And if we doubled that, it would be a little under $300,000. So that was a silly question. Let's answer the last question. How much interest was earned? Well, in order to answer how much interest was earned, I need to know how much money did I pay and how much money did I get. I know how much money I got. That's the future value. And give me 1 second to get rid of that. That's bothering me. We know how much money we made. We made $148,877.43. But how much did we pay into this? Not $250. The amount that we paid into this was $250 a month per month for 25 years. So we paid, and I'm going to go into the text box here. We paid $250 a month times 12 months a year times 25 years, which is equal to, I really don't need a calculator for this calculation, but I'm going to, $75,000. So that's how much we actually paid into this by making 12 monthly payments of $250 per year for 25 years. And so the interest is what we ended up with, $148,877.43 minus the amount that we put in, which was $75,000 and no cents. And so what does that equal? I shouldn't need a calculator for this equal. I'm a little bit embarrassed, but I can't, especially since I just typed it in incorrectly. Wow. Looks like we made $73,877.43. We didn't even double our investment. But, you know, I mean, still, it's an extra $73,000, almost $74,000 by paying $250 a year, $250 a month for 25 years. All right, so it's a pretty big formula, and it takes some getting used to. But just be very careful when you set it up because of the size of the numerator and the denominator. I strongly recommend extra parentheses. And of course, the exponent being more than a single number, I recommend parentheses there as well.